In the next section, we will conclude our discussion on water balance, including the concentration and dilution of urine, and outlining the concept of free water clearance. Free water is defined as distilled water that is free of solutes, or solute-free water. In the nephron, free water is generated in the diluting segments. This is where solute is reabsorbed without water. Remember, the diluting segments of the nephron are the water-impermeable segments. Normally, this is just the thick ascending limb and the early distal tubule. In the absence of ADH, the late collecting duct can also be a diluting segment. Measurement of free water clearance, referred to as C subscript H2O, provides a method for assessing the ability of the kidneys to dilute or concentrate the urine. The principles underlying this measurement are as follows. 1. When ADH levels are low, all the free water generated in the thick ascending limb and early distal tubule is excreted. This is because it cannot be reabsorbed by the collecting ducts. In this case, the urine is hyperosmotic and free water clearance is positive. When ADH levels are high, all the free water generated in the thick ascending limb and the early distal tubule is reabsorbed by the late distal tubule and the collecting duct. In this case, the urine is hyperosmotic and free water clearance is negative. Because water is reabsorbed, the clearance is negative. Free water clearance is calculated by the following equation. Free water clearance is equal to the urine volume minus the clearance of osmoles. The clearance of osmoles is determined by the same equation that we used previously to calculate clearance of any other substance. That is, the concentration of osmoles in the urine times the urine flow rate over the plasma concentration of osmoles. Once again, C subscript H2O is free water clearance measured in milliliters per minute. The V is the urine flow rate in milliliters per minute. C subscript osms is the clearance of osmoles in milliliter per minute. The urine concentration of osmolarity is the urine osmolarity measured in milliosmoles per liter, and the plasma osmolarity is also measured in milliosmoles per liter. Let's walk through a sample problem to measure free water clearance. A man has a urine flow rate of 10 milliliters per minute, a urine osmolarity of 100 milliosmoles per liter, and a plasma osmolarity of 290 milliosmoles per liter. What is this free water clearance, and what is its significance? The man's free water clearance is calculated as follows. Free water clearance is a positive value, which means that free water is being excreted. The solute-free water generated in the thick ascending limb and early distal tubule is not being reabsorbed by the collecting duct. Rather, it is being excreted. This situation occurs when circulating ADH levels are low. As in water drinking or central diabetes insipidus, or if ADH is ineffective, as in nephrogenic diabetes insipidus. With regard to the calculation, it is as follows. Recall that the free water clearance is equal to the urine flow rate minus the clearance of osmoles. The clearance of osmoles is given by the urine concentration of osmoles times the urine flow rate over the plasma concentration of osmoles. Substituting the numbers given in the problem, we can see that the free water clearance is 6.55 milliliters per minute, a positive number. Free water clearance can be 0, it can be positive, or it can be negative. The explanations for these values are as follows. Free water clearance is 0 when no solute-free water is excreted. Under these conditions, urine is isoosmotic with plasma, also referred to as isostenuric. It is unusual for free water clearance to be 0, but it can occur during treatment with a loop diuretic, where sodium chloride reabsorption is inhibited in the thick ascending limb. When solute reabsorption is inhibited in the thick ascending limb, no free water is generated at this site. If free water is not generated, it cannot be excreted. Therefore, the ability to dilute the urine during water drinking is impaired in a person who is treated with a loop diuretic. Likewise, the ability to concentrate the urine during water deprivation is also impaired because loop diuretics will interfere with the generation of the corticopapillary osmotic gradient by inhibiting the sodium-potassium 2-chloride cotransport and countercurrent multiplication. Free water clearance is positive when ADH levels are low or when ADH is ineffective and the urine is hypoosmotic. The solute-free water, which is generated in the thick ascending limb and early distal tubule, is excreted in the urine because the late distal tubules and collecting ducts are impermeable to water under these conditions. This is outlined in box 6-3 on page 296. Free water clearance is negative when ADH levels are high and the urine is hyperosmotic. All the solute-free water generated in the thick ascending limb and early distal tubule, and more, is reabsorbed by the late distal tubules and collecting ducts. Because free water clearance negative is a cumbersome term, the sign is reversed and is called free water reabsorption. Let's walk through another case of central diabetes insipidus. A 45-year-old woman is admitted to the hospital following a head injury. She has severe polyuria, producing 1 liter of urine every 2 hours, and polydipsia. She is drinking 3 to 4 glasses of water every hour. During a 24-hour period in the hospital, the woman produces 10 liters of urine containing no glucose. She is placed on overnight water restriction for further evaluation. The following morning she is weak and confused. Her serum osmolarity is 330 milliosmoles per liter. Her serum sodium concentration is very high at 164 milliequivalents per liter, and her urine osmolarity is 70 milliosmoles per liter. She is treated with DDAVP by nasal spray. Within 24 hours of initiating the treatment, her serum osmolarity is 295 milliosmoles per liter, and her urine osmolarity is 620 milliosmoles per liter. Let's explain the findings. Following overnight water restriction, the striking observation is that the woman is still producing very dilute or hypoosmotic urine despite a severely elevated serum osmolarity. Diabetes mellitus is ruled out as the cause of her polyuria because no glucose is found in her urine. The diagnosis is that the woman has central diabetes insipidus secondary to a head injury. The woman's posterior pituitary gland does not secrete ADH, even with a strong osmotic stimulus such as a serum osmolarity of 330 milliosmoles per liter. This absence of ADH results in a profound disturbance of water reabsorption. She is unable to produce concentrated urine. Her distal tubule and collecting ducts are impermeable to water in the absence of ADH, therefore no water can be reabsorbed by these segments, and her urine remains hypoosmotic at 70 milliosmoles per liter. Because she is excreting excessive amounts of free water, serum osmolarity and serum sodium increase. The high serum osmolarity is an intense stimulus for thirst. This will cause the woman to drink water almost continuously. The woman is treated with DDAVP. The woman is treated with DDAVP, an ADH analog that activates the V2 receptors on the principal cells. When ADH binds to the V2 receptors, adenyl cyclase is activated, cyclic AMP is generated, and water channels are inserted in the luminal membrane, which restores water permeability of the principal cells. After initiating DDAVP therapy, the woman produces hyperosmotic urine, restoring her serum osmolarity to normal, in conjunction with drinking adequate water. This concludes this section.